start the webinar. Welcome everyone. Welcome to today's lunchtime webinars where you're going to get an introduction to heat pumps. I'm sure it's a subject that you've been hearing a lot about. We're hearing more and more about heat pumps, aren't we? And so today hopefully is to tell you what they are, the basics of how they work and when they're suitable in a church context, and maybe even more importantly, when they're not suitable in a church context. Before we get going with heat pumps, you probably know I always start my webinars with a trailer for the upcoming attractions. I know that's a very busy slide. We've got a lot of webinars this autumn. There's one, I think, every week from September through to Christmas. We've got a whole load of topics in the Net Zero Carbon series. The first and really important of those is environmental fundraising. So we've got two different sessions on fundraising at the beginning of September, one on schools, a repeat of today's session on heat pumps. So if you get to the end of today and wish that a colleague had come along, then they can book on to the next time this is running. And we've got some really interesting topics then coming up. One on conservation pitfalls and how to avoid them en route to net zero. So particularly useful if you're dealing with historic buildings. One on getting to yes for your environmental projects. So that's all about the faculty system and how you might be able to best present your case and get through the faculty system. And then one that's touching on a kind of awareness around embodied carbon in our building projects. So that's called Finding the Balance. And it's about how we can think about the carbon invested in our projects as well as what we save on our energy bills. We've then got a repeat of our 3 Eco Church webinars if you didn't make it along over the last few weeks. They're getting started, gathering momentum, and the link to net zero. And then during the season of creation in September, we've got a series of webinars which are more on the theological and worship side around Forest Church, theology of climate change, let all creation sing, and climate action is mission. So you've got quite the menu there to choose from. When I finished with the housekeeping, I'll put a link through to where you can book on to the webinars into the chat. In terms of the housekeeping for today's webinar, it's the usual. If you've been along to one of these before, I will be using the Q&A for the questions rather than the chat. So you need to move your mouse around, find the Q&A, and that's where you type in your question. You can also see other people's questions and you can click the thumbs up next to the ones that you're most interested in. Those will rise to the top. And when Mark has finished speaking, we'll focus on the questions in the Q&A. After today, I'll be sending you around the slides and I'll also send you any links that are shared in the chat. We record these sessions and we make them available on our website on the same webinars page where you book on. Normally it takes me a few days to get the recordings up, so bear with me. Most importantly, our guest speaker today. So we're hearing from Mark Taylor from Tailor-Made Energy Solutions, a very experienced chartered energy manager, a couple of decades of experience in dealing with energy efficiency, heating. And I heard Mark give a webinar similar to the one that you're going to hear today on behalf of the Energy Managers Association. And I thought it was really, really useful. So I contacted him and said, could he tailor it for a church audience and come and run it for us? And if you haven't come across me before, Catherine Ross, I'm one of the people that works on the Church of England's Environment Programme, and I'm based in the Cathedral and Church Buildings team. Right, let me stop sharing my screen and hand over to Mark to bring his slides up and take us away.
Okay, so hopefully you should be able to see my slide pack up there.
Perfect.
So we will get into this straight away. Thank you for that, Catherine. I'll skip my slide. I think your introduction was pretty good. So, okay, so heat pumps. It's a bit of a topic of the month and topic of the year, I think probably at the moment. A lot being talked about it, and I think probably being touted as the great hope for decarbonising our heat sources in this country over time as we try and move away from gas. So just a little bit of background really. As we get more and more renewable electricity generation on our grid, and we've obviously still got quite a chunk of nuclear generation, the grid is becoming cleaner and cleaner, and we've now reached a point where our electricity grid, the emissions are around about the same as it would be from burning natural gas. So we have now reached a point where electricity being used to heat our buildings has actually come to a point where it's pretty much about even with gas. And over the next few years, as more and more renewable energy comes online on our electricity grid, it will actually be cleaner to generate our heat from electricity than it will be from gas. Gas is pretty much pure methane. It's not going to change that much in the short term. So it's making electricity more and more attractive to heat our buildings, and importantly, I guess for the purposes of today, to reduce our carbon footprint. And it's only going to get better over time, because as grid electricity lowers and lowers until eventually it is almost pure renewables, then electrical heating will carry either very low or no emissions at all. So while we've had heat pumps have been around for quite a number of years, it's not a new technology, and they have been deployed in certain buildings over time. The decarbonisation agenda really now is driving their increased use, and the government has actually decreed that they want to see over 600,000 a year of these being deployed within about 10 years. So it's really that decarbonisation of the grid is what the key element is in their use. And heat pumps basically are just something like our fridges and our freezers that we have in our houses, but working backwards. So they are reverse refrigeration systems. So in theory, they can create multiple units of heat, multiple kilowatt hours of heat for each kilowatt of electricity that they consume. So they are a heat pump, so they do consume electricity, but in theory, they should produce much more heat than they actually take in energy. So that means they're defined as producing renewable heat, okay? So these are reverse refrigeration systems, and I'll just show you a quick diagram, a bit of an outline of how these work. With our fridges and our freezers at home, what they do is they actually take heat out from inside the fridge, and then they expel it out of the back of the fridge. So you hear that compressor running, the little motor, and if you put your hand behind the fridge or freezer, it is always warm. That is where the heat is being expelled. What we do with heat pumps is the exact opposite. We are trying to take heat from an outside natural source and extract that heat from the environment around us. But instead of refrigeration, we put that back out into the environment. We will put it into our sealed boxes, our rooms, our buildings. So it actually just works the exact opposite way to what a classic fridge has. So this technology has been around now for 100 years or more. In terms of the way that the units are set up, you've got an evaporator and a condenser, exactly the same as any fridge or freezer has, and a compressor and expansion valve, again, exactly the same as they do, but it's just in reverse. So on the left-hand side, we have got our heat source, and I'll come to what those sources will be in a minute. We've basically got a refrigerant that runs inside this system, so it's a sealed system, and that refrigerant evaporates at very, very low temperatures. So even relatively low outside air temperatures in the middle of the winter, for instance, can actually produce heating for our buildings. So basically, the refrigerant absorbs the heat from the outside air or whatever the source may be. As it absorbs the heat, the liquid actually turns into a vapor and starts to travel around the system. The compressor then compresses that vapor, sort of liquid gas mixture. And what is already warm, because it's already been evaporated, it gains heat. It gains even more heat as it goes through the compressor, and it gets compressed, and it eventually turns into a pure gas. That gas is now a hot gas, and on the right-hand side of this drawing, that hot gas now gives up its heat to start heating our water or our air, whatever it will be. And that gas is by now giving up quite a lot of heat. It loses its heat on the right-hand side as it gives it up to our systems. As it gives up the heat, it drops back into a vapor type of sense. And once it drops down to the expansion valve, the pressure gets dropped and it returns back to its liquid state, and it just carries on and doing the whole cycle again. So basically, a fridge would work exactly the opposite way. Takes the heat out in the useful heat terms in the right-hand side in this case, and the external side at the back of the fridge is the left-hand side. Now we've got an external heat source, and we pull that heat into our buildings. So the key thing really about heat pumps, that idea of them actually creating far more heat than the electricity they used, That is the absolute key measure with a heat pump, and it's termed the coefficient of performance. You'll hear people talk about COP all the time with heat pumps, and you hear people talk about figures and numbers and say the COP is this, COP is that. That is the coefficient of performance, and that is the amount of heat units get produced for each heat unit, each unit of electricity that the heat pump actually absorbs. And what we're looking for ideally is for that COP to be around 3 to 4. If you're going to get a COP that high, so 3 or 4 units of heat generated for every unit of electricity used, then the carbon benefits are very large against pretty much all fossil fuels. Okay, so that's where the benefit comes from using a heat pump. One thing to be aware of, and it is the one downside of heat pumps immediately, is that as electricity is around 4 to 5 times more expensive than a unit of gas, the financial case to make for heat pumps against gas boilers in particular can be quite a difficult one to make. There is quite the possibility that you will install a heat pump and actually put your electricity costs up, not down, and you will actually be paying slightly more for your heating afterwards than you were before, but you will get that big carbon reduction benefit. The other thing as well is that heat pumps at the moment do have a much higher initial capital cost than things like gas boilers. So again, the economics are not necessarily the easiest case to make. It's a much easier business case to make if you are burning something like LPG or fuel oils or such like that. Natural gas is very, very cheap, so it is a difficult business case to make. Much easier to make against the off-grid type energy supplies, such as your LPGs and your fuel oils. Just be aware that the refrigerants that are used in a lot of the heat pumps at the moment, they can have quite a high greenhouse gas warming potential. So if you do get leakage out of these systems, the same as any air conditioning type system, your emissions actually can be quite bad because some of those are a lot worse than CO2, but that shouldn't in theory happen. So the way heat pumps work is they either will produce hot air or hot water more often from a relatively constant low temperature external source. And there are 3 main types of heat pump that you're going to come across. Ground source heat pumps, where literally we absorb the latent heat that's sat underneath the ground. It either uses looped pipe, miles and miles of looped pipe, I'll show you a photograph shortly, or you could actually drill a borehole right down and pick up that heat from much further down in the earth. There are air source heat pumps, which are probably the most common type used and the easiest to install, and they literally will pull heat out from the surrounding ambient air all year round. Even when it's -degrees outside, they can still pull heat out even then. And we've also got water source heat pumps, probably the least deployed, and they can absorb heat from water bodies such as lakes or rivers. And these are usually fairly consistent temperature all year round. And again, they can use that heat to produce our heat for inside our buildings. Just be aware that the current generation of what's known as vapor compression heat pumps, which is the cycle I just showed you, they do tend to be designed for lower temperature heat than the standard gas boiler will produce. So at the moment, they are not a direct like-for-like swap. If you do that, you are likely to struggle for heat in your buildings. The heat pumps can produce higher than that, but their general use is for a lower temperature water. We tend to produce 70 to 80 degree water from our gas boilers to run in radiators and such like typically. That is not the usual temperature range that a heat pump will tend to run at. Heat pumps are rated for their thermal output. When you hear about people talking about heat pumps, size-wise, if somebody says it's a 45 kilowatt heat pump, that means it will produce 45 kilowatts of heat nominally. So that is the same as a gas boiler would be rated at. However, just be aware that is their maximum capability at their optimum running conditions rather than the normal output. So for hot water systems, realistically with the current heat pumps we've got, they tend to run to produce hot water at really less than 60 degrees C. So they are ideal for applications such as underfloor, where you have generally got about 35 to 50 degree hot water in those kind of systems. They are a perfect match for those kind of systems. They are not a good match currently for the standard type of radiator systems where you will be running 70 to 80 degree water inside them. They can produce those kind of higher temperatures to match gas boilers. They will do it. However, at that stage, that magic COP, the coefficient of performance, that will drop like a stone. And so the efficiency of the units at those higher temperatures will be very, very poor. And that will potentially create very, very high running costs. If you've got a COP of perhaps only 2.5, which will be created when you start running at 70 or 80 degrees, you will probably find against natural gas that a heat pump will be 3 to 4 times more expensive to run. So you do need to get them in that right application. This is a couple of pictures just to give you an idea what they look like. On the right-hand side, what you can see is a looped ground source. So what they do is they bury a very long length of pipe in these loops, as you can see, only about 1 meter down under the ground. But at that level, we've got a fairly consistent 10 or 11 centigrade temperature all year round, just at that little level under the ground. But you obviously do need an awful lot of space to do that. There is quite often literally miles of this underground piping. So as you can see, there's a lot of big trenches needed to get the loops in there to absorb the heat. The left-hand side is a picture of a borehole going in, and obviously you need less space for that because it goes straight down. But there are obvious civil engineering challenges, and you need the space to do that, and geology has to be correct as well for you to work a ground source borehole. So basically, in that case, the refrigerant and the water mix is put straight down into the borehole. It picks up the heat while it's down there and comes back up to be used. In terms of air source heat pumps, this is what the outside unit looks like. Very, very similar to a standard air conditioning system, in that you'll have a kind of external unit and an internal unit. This is what the external unit might look like. This is what the 3 parts of it look like, and this is the installed indoor unit. So on the top left there, you can see you've got your standard outdoor unit, the evaporator. The unit, the little one on the floor, which is your condenser, that is the one that in this particular case with an air system, which would put the hot air into the room, just like a standard air conditioning unit. And this is your actual heat pump unit sat here. And this is a fully installed one sat in a plant room. And this one has also got a big tank of hot water as well. Heat pumps are not quite like natural gas boiler systems where you switch them on and within 5 or 10 minutes you've got heat and the room's already getting warm. Heat pumps take a little bit longer because the temperatures are lower, and the way they work, they don't produce that kind of instant heating. So you tend to have heat pumps running for longer hours sat in the background, just giving a lower level of heat to heat your buildings. They're operated in quite a different way. And very often having a big hot water store like this, a big tank, that enables them to run a lot more effectively because they're basically just heating up a volume which is then available to be used in the building. So heat pumps can deliver either warm air or hot water, but to do warm air, you would either need a warm air circulation system already existing. So it might not suit existing buildings, although it may if you've got the kind of underfloor ducting, or you will need the sort of new air conditioning style units to be installed. So they would be mounted up on the wall. And we've got an example of that in a church later on that I can show you. Both air and hot water heat pumps will obviously have varying coefficient of performance throughout the year. As the source temperature changes, then obviously the amount of heat that can be produced and the ease that heat is produced will also change as well. Air source heat pumps are the most prone to that because obviously we could have 20, 25 degrees outside air temperature in the summer. Very easy to develop hot water from that. But we could be down to minus temperatures in the winter. The units work a lot harder. Ground source is a lot more stable because the ground tends to stay much more sensible temperatures all year round. Water source, again, reasonable. The temperatures do change a little bit, but nothing like the air source heat pumps. So again, beware of those kind of changing levels. So you will have a varying COP throughout the year, but all heat pumps are quoted with a seasonal COP, so you know what that looks like when it's averaged out. There are new generation of heat pumps kind of coming along, as always with these things, they get very rapidly developed. And these are starting to use different refrigerants in them, such as ammonia or CO2. And they are likely to address some of these issues that we've seen with the existing ones. And they can start to produce higher temperatures, potentially up to around about 110, although probably around 80 again would be needed to still maintain that good COP. These are tending to be sort of heavy commercial units at the moment. The very large type of units. There's a massive scheme going in on the Clyde up in Glasgow, where they are putting multi-megawatts in and using the Clyde River as the heat source, a water source, the heat pump. And those units are enormous and are going to produce some higher temperatures. But those will eventually filter down into our smaller building use as well. But as with all heat pumps, however, the key thing always is they will be the more efficient, the lower the temperatures they are operated at. They don't have to work so hard, and so that COP is always better. And obviously, because they run things like CO2 as their refrigerants, their greenhouse gas warming potential, the damage they could do if that gas escapes, massively lower than some of the standard refrigerants we have now, where the greenhouse gas warming potential is thousands of times worse than CO2 could be. So in general, heat pumps will work very well in new builds because they always tend to have much higher levels of insulation and air permeability. They don't leak, they have good windows, high levels of insulation. So the characteristics of heat pumps are taken into account really at the design stage. So they can really work really well in those, virtually no other heating required, excellent for brand new builds. Your portfolio, probably not quite so good. The older buildings, not necessarily got those same level of insulations, or if you've got a really big old stone church with really thick walls, again, it might suit reasonably well. They can supply radiator type systems, but what you tend to find is either the levels of insulation in the building have to be massively improved to allow the existing radiators to be used, or you might well have to have all new radiators put in, and they will be much larger surface area radiators. So they will run at a lower temperature to suit the heat pump, but because they've got a bigger surface area, the same amount of heat is actually put into the room. So that may be something that might have to be done, as well as you might have to change your heat emitters as well. Heat pumps can be very expensive and very awkward to integrate into existing heating systems, because mirroring the existing parameters is not easy with a heat pump. They don't work in the same way. So it can make them expensive to run and potentially unreliable if you just try and bolt them in. I've come across quite a lot where people have just switched them off, found they're very expensive because they've assumed they are bolt in straight for a gas boiler, and they are not, unfortunately. Some existing buildings with gas boilers, you may well have higher water temperatures already than required. So you may actually find that a heat pump can suit, and actually your costs will tumble as well, just because the gas boilers were always being run at too high a temperature. So it's always worth checking to see if actually what the temperatures you run at now are the real ones you need, because it might be that your building does suit a heat pump, but it just doesn't look like initially because of the temperatures you run your existing gas boilers at. Some buildings we have to accept ultimately may well need some kind of hybrid system, where the heat pump perhaps supplies lower grade heat for a part of the year, but you may retain your gas boilers or have another heat source which will supplement it during those colder or high demand periods. Now that might only be a few weeks a year, but you might well find that you struggle with a heat pump all year round, and it might be that you have to have a supplementary source of heating. Just be aware as well, probably not an issue so much mostly for your kind of standard church or place of worship, but for your other buildings where you may have domestic hot water supplies, because a lot of other activities happen in there. Your standard water that comes out of your taps and showers for your sinks and such like, that does need to be provided at about 60 degrees C to avoid Legionella issues. And obviously, if you're going to ask a heat pump to produce domestic hot water, it will be up around that 60 to 65 degree temperature, where straight away the heat pump will become quite inefficient. So you do need to be aware that if your boilers existing are producing domestic hot water as well in any volume, you may well find that you want to do something different to that and move to something like point of use heating a little over the sink taps and heaters where they only heat water when it's needed. So you can drop your heating system temperatures to suit a heat pump. So to get the most out of a heat pump, and the crucial things really is you need to maintain that manufacturer's COP. All heat pumps will have a good COP when they run at the right sort of application. And really that's what needs to be done. You need to understand the manufacturer's recommendations for COP and maintain them, or the value is gone and they can be expensive to run. Just be aware that very often the figures quoted for heat pumps are at high outside air temperatures as a source and relatively low achieved water temperatures. So they don't really reflect what the genuine COP would be. They'll quite often quote things like air at 20-degree temperature, so a nice summer's day, and water temperature being produced of only 35 degrees C. And so the COP will look brilliant at that stage. But in reality, nobody runs at 20 degrees C all year round source temperature, and they don't produce 35-degree water. You'll be looking at 55, 60 or so. And straight away, that means that COP is lower. There's a number of key areas you need to consider to maximize your efficiency, and these really need to be built into the design and consideration for heat pumps if you're looking at them. The flow and return temperatures from the heat pump, so that's the temperatures that the water temperature they produce, and the temperature it then comes back to the heat pump to be reheated again, they should be as low as possible. The lower you will get them, the more efficient your heat pump will be. So you need to make sure that you're accurately reflecting what temperatures are required in your buildings, rather than necessarily what those current values are. The lower you can make them, the better. There's also a benefit as well in keeping the difference between the flow and return temperatures low. So you don't want a massive difference in the water temperature coming back to that going out. That makes the heat pump work very, very hard. So the closer you can get, that increases efficiency as well. And obviously having a higher source temperature, whether it's air, ground or water, the higher that source temperature is, the easier it is for the heat pump to raise that to a higher temperature again. And so obviously that is going to be better. So as we said, outside air does get cold. Ground or water temperatures are higher, but they are much more expensive systems to put in. So the heat pump COP will generally be higher on ground source and water source heat pumps. Obviously, a lot of these can be difficult in the UK because when we got our lowest source temperatures in the middle of the winter is typically when we've got our highest heating demand. So heat pumps don't necessarily provide the best fit, but if they can be maintained and run at a good COP, they can be very effective in many buildings. So just to give you an idea of how these work, and this is a typical graph that you'll see associated with heat pumps to show you how they work and how efficient or not they may be. Looks complicated, but this is relatively simple. We've got our coefficient of performance down the left-hand side, and we have got our outdoor air temperature on the bottom. And what we've got is a series of curves based on the water temperature that we want to achieve. So if we just take, for instance, the blue line, that is a water temperature being achieved of 35 degrees. Okay for underfloor heating, just about the bottom end of underfloor heating. And what we can see is if we have got a 0 degree outside air temperature, and on our blue line, we have, even at 0 degree outside air temperature, we've still got a COP, which is not far short of 4, about 3.75. So that would be a very effective unit. However, as we've said, 35 degrees, pretty low water temperature really, and probably the brown line is more accurate for what most systems would want, at least 50 degree water temperature. And even then, that's obviously low for radiator systems. If we now look at what 50 degrees is at 0 degrees outside, now we're looking at a COP which is about 2.5, so not great. However, if we then take those same numbers and say, well, it's going to be a 14 degree outside air temperature, back on our blue line at 35 degrees, we can see our COP now is up around about 4.5, nearly 5. That would make that a very, very efficient system and a very cost-effective system to run. So you can see that, at times when our outside air is at a reasonable temperature, these are really good. And even if we're producing 50 degree water, we would still be up over 3, probably 3 to 3.25 as a COP. So again, a pretty efficient system that would work reasonably well. So it's very, very important that you understand what temperature water you want to produce and the likely range of outside air temperatures in this case that you will encounter, because that will tell you how successful that COP will be. Now, it doesn't really matter too much if there's a couple of weeks in the year when the COP dives down and maybe runs at 2. What you're looking for is that average of over the year. So what your average temperatures are in your region during the year will probably give you a pretty good idea of where you would sit on this type of graph. This is another one, slightly better unit. Again, we've got some different colors on here. It's a bit clearer. And again, what we can see is if we have got 50-degree temperature on our green curve, on this particular one, if we've got, say, a 20-degree outside air, we have got a COP of 3, which would operate pretty well. But if we're looking to, say, do 60-degree water, we can see now that in the UK, on average, we'd be in this region somewhere, which immediately puts us down in about the 2.25 region. That would be an expensive heat pump to run, very expensive. You really need to be up in these kind of regions here for COP. So just a couple of other considerations if you are looking at heat pumps. They are rated in thermal load, but they also obviously need quite a potentially heavy electricity supply. So you do need to be aware of what the available electrical capacity is of your building if you're adding a heat pump. And in general, a heat pump will probably use about 1/4 to 1/3 of the electrical load that it's rated at in heat. So a 45 kilowatt heat pump will probably be in the region of around about 10 to 15 kilowatts of electrical load. But these can be quite big, obviously. If you've got a couple of 100 kilowatts of heat pumps going in, you will be looking for 50 to 60 kilowatts of electrical load. So just be aware of whether that does suit the buildings. Are you going to have a total reliance on heat pumps for all of your heat? And if that is the case, that means you are sizing your heat pumps for that absolute maximum demand day, the same as you would have on a boiler. And by default, that means a lot of the time you will be running at part load running regimes. So you might have multiple heat pumps and only one will run. So you may sort of consider, whether it's worth going purely for heat pumps. And do you actually have multiple units installed then to cover redundancy? So if one breaks down, do you have a standby as such? And also some of the heat pumps, just like air conditioning and other things, they run through defrost cycles, just like our fridges do. And while they're on defrost cycles, they don't necessarily produce heat. And that defrost cycle can be for 15 to 30 minutes. So sometimes people have extra units in. So while one is offline defrosting, the second unit can be running to replace it. And ultimately, do you consider some sort of hybrid system? You might keep your gas boilers, and that can be used for sort of peak loads and those really, really cold ones, your beast from the east type conditions. And also then that would enable you to probably have quite smaller heat pumps, make them much more effective capital wise. And you run a bit of a combination of the two potentially between them, which can produce all the heat you want, but with minimal gas use. A lot of hybrid heat pumps have been proposed over the last few years on the basis of stopping the electrical heat pump at the peak tariff times to try and make them avoid high costs. But unfortunately, that is disappearing because that benefit will go in 2022. So if somebody does try to say to you, you can switch a heat pump off to avoid high costs certain times a day, as of April 22, that will not be the case. That disappears. So just to give you a bit of a guide in terms of costs of heat pump, difficult to do because the cost of the heat pump installation is one of the key things, and that varies enormously depending on where you can locate them, how easy it is to integrate into your existing heating, the pipe runs, the cable runs. So it is very difficult to give a sort of cost on the installation side of it. That would have to come when you look at it. But just to give you a bit of an idea, a domestic size heat pump, so that's about 10 to 14 kilowatts thermal output, an air source heat pump probably costs you around about 10 to 12,000 pounds fully installed. Against sort of 2 to 4,000 pounds for a gas boiler, that's quite expensive at the present time. For sort of larger commercial systems, larger air source heat pumps, say around about 45 kilowatt thermal unit, that'll cost you around about 25 to 35,000 pounds. A larger sort of 80 kilowatt unit may be up around about 40 to 50,000 pounds. What they then do is to basically stack those up to create larger systems. They tend not to put sort of single big heat pumps in down at the lower end. You might end up having 3 or 4 of the 80 kilowatts in or something, or 3 or 4 of the 45 kilowatts in to make up something like 150 or 200 kilowatts of thermal demand to match gas boilers. Okay, so you multiply in those prices to get the higher systems. For a ground source system, something like an 80 kilowatt system might cost you around 80 to 90,000 pounds purely for the heat pump. And then you've got either a borehole or the civils work of the looped ground pipe as well on top of that. Installation costs, as we said, vary massively depending on the type of pump, whether it's being integrated into an existing system, is it brand new, it can just be laid in. All of those will dictate really whether that installation cost is higher or lower. Ground source heat pumps, as we said, obviously carry a much higher cost due to the civil engineering which is involved in their installations. And there's things like geological surveys and such like, even just to see if the ground conditions suit as well. In terms of funding for heat pumps, we did have the Renewable Heat Incentive, the RHI, until recently for commercial applications, but that closed this April, so that is now shut. The domestic one carries on until April next year. There is a replacement proposed, which is called the Clean Heat Grants, which has been consulted on, but nothing put back out yet. But it won't be a pence per kilowatt hour scheme like the RHI was. It will be an upfront payment, which is being estimated to be around £4,000 on a voucher-based system. So the voucher will go to your heat pump installer. And the current consultation has actually proposed a qualifying limit as well of 45 kilowatt thermal, because the support is being targeted really more at smaller systems. And the grants will only be available for pure heat pumps. So the grants won't be issued for any kind of hybrid system which uses fossil fuel as a part of it. So it's got to be used only for producing heating or hot water for those purposes as well. Only one heat pump in theory will be able to be claimed per building as well. So if you've got 3 or 4 heat pumps installed, you'd only get money for one. But multiple units can be claimed for in accommodation style blocks, which probably won't be of much use to most of you. And there will be a requirement to have a minimum seasonal coefficient of performance, a SCOP, of 2.8 is required. So the manufacturer's data should say that unit can run at 2.8 all across the year at least. Doesn't mean it will, but it can do under those right circumstances. So just to give you a couple of examples where heat pumps have gone into churches. This one is at Long Ashton Church in Bristol. They actually had an air source heat pump installed in 2014, and it replaced basically an old oil-fired system, so a good one straight away. The unit is sized at 120 kilowatt thermal output, and that means it uses about 32 kilowatts of electric. But they've also got 9 kilowatts of solar installed on their roof to help with the extra load. And they've installed a very large hot water system as well, storage system, so they can produce lots of hot water with the heat pump, and then that absorbs any kind of peaks of heat demand that they've got. They are currently feeding low temperature convection heaters with this one, so it's an air system with a water temperature at around about 55 degrees, so pretty reasonable for a heat pump system. The normal church set point, they tell me, is around about 12 degrees. So they basically just maintain the building at 12 degrees constantly. But then they lift it for the various church services that they have. So the day before, they will lift the set point, but they only try and maintain around about 12 degrees generally. They're not claiming any RHI for the system at all. So it was done without any grant funding of that name. They couldn't give me any firm COP figures available, unfortunately. But they have estimated their running costs to be pretty similar to what the old oil system was. And that's roughly what you'd expect. There will be a parity with the old oil type systems because they're quite expensive fuel-wise as well, whereas gas is much cheaper, natural gas. So excuse the photos, this is what they provided me with, but that was the unit being delivered and offloaded, and obviously they had to take it in over the wall to get the outside unit in. They built this little compound by the sound of it, which is outside, just sort of in the churchyard area somewhere, but they built that outside. I think actually that is some gravestones in the floor, so you can see it was sort of put right against the wall in the churchyard. So that was the external units, the ones that gather the heat. This is their big water storage cylinders that they've got inside the building. That was it for that one. And then the second example we've got is St. Nicholas Cathedral in Newcastle. Now this is a project which is currently underway, so I've got no photographs, I'm afraid, because it's not actually there at the moment, not completed. But they are installing 2 air source heat pumps, recently started to be installed. This is being done as part of much larger works, apparently, to provide new heating in the nave area of the church. And that is going to supplement existing gas boilers that they've got in there. They've got 2 units going in sized at 14 kilowatt thermal each and 4.8 kilowatts electrical demand. And they thought they might have got them in just in time to get the RHI. The system here will be feeding a brand new underfloor heating system. So the nave was just having a new floor put in anyway. So they've taken advantage of that, put an air source heat pump in, and they're feeding underfloor heating system. And the water temperature will be around about 50 degrees C. So again, absolutely ideal for a heat pump. The remainder of the church in this particular case will still be fed from their gas boilers. And they're also going to be then used as a backup system for the nave if there are any problems. So you can see by the size of it, it's not a big system, and it's only going to do a relatively small area of the cathedral. Again, the normal church set point that they tell me they hold it at is around about 16 degrees. And again, they will bring that up if they need to for specific activities, but they're not deliberately not trying to keep these buildings particularly warm or high temperatures. They are looking to get a COP of around about 3 from all the design that's been done. So they know they will probably see a bit of an increase in their overall running costs because at 3, you would need probably more like 4 COP to be even sort of relatively cost neutral with gas. And the last example we've got is All Saints Church in Somerby. They actually had 7 air source heat pumps installed in 2009, so going back quite a way, this one. And again, they replaced an old oil-fired hot air system with hot air blowers blowing hot air around the church. Apparently way beyond economic repair, so they needed something else. Now they've actually got 5 units that are 6.3 kilowatts and 1 at 2.8. As well as 1 at 3.7 thermal. So they're all little bits of different pieces, different size, and dotted around the church. Don't know if RHI was claimed on this one, although I suspect not. And the systems then actually provide hot air into the church via 7 hot air units that have actually been installed inside the church. So they blow hot air into the church. And this is actually the only heating in the building altogether on this one. I couldn't get any information, I'm afraid, on the temperatures they were hoping to achieve or the COP. I'm not sure they actually were measuring it, to be fair. But just to give you an idea where the installations are, perhaps not great. I think we probably all agree on that one, that the units were installed in the churchyard and they're literally in amongst the headstones. So that's the some of the external units in this case. There's another 3 as well elsewhere. So those are the units which are pulling the heat out of the atmosphere and sending it into the church. And then inside the church, basically, they've got 7 of these on the walls. So that's just like a sort of standard air conditioning unit. I guess it probably would be a bit of an issue in a lot of listed buildings that just putting something on the walls wouldn't necessarily be something you could do. But that's what this particular one has done, and that is the sole heating now in that building is just those 7 units up on the walls. Okay, so that's about it for the presentation. So we'll take any questions, Catherine.
Brilliant, thank you so much, Mark. If you want to end your screen sharing, and then we can move on to the Q&A. So for everyone, if you find the Q&A by moving your mouse around, you'll see there's already a lot of questions in there. You're very welcome to add another question, or what you might want to do is skim down until you find one that covers the same ground and vote it up, because I can see we've already got a lot of questions. So the first one is, it's about finding good advisors. Could you point us in the right direction to find good advisors or surveyors to advise whether heat pumps are appropriate for our context? Generally, I point people towards CIBSE if they're looking for a specialist in this area. Is that what you would recommend, Mark? Where do we look for someone who knows about heat pumps in the local area?
To be honest, it is a difficult one, and it's one that people get caught out on. Unfortunately, renewable energy has become a bit of a game for a lot of installers, because they just jump from one sort of technology to another. These guys all started off doing solar. Very often, to be honest, they were kind of plumber type people and people who were doing a bit of something else. They saw solar and thought, that's an easy one, we'll do that. They did that for a while until the money ran out, and then they jumped over to biomass, and then they did that for a while until the money ran out. And the latest one, really unfortunately, is heat pumps. So there are a lot of people out there who will say that they install heat pumps. That is not necessarily true, and these guys very often don't know what they're talking about, and they will sell you a heat pump quite happily and install one. It doesn't necessarily mean it's the right application. They will install it correctly so that it is done properly. There are bodies which regulate some of this stuff, and to be honest with you, what I would say bottom line is, if these guys aren't on one of the registers, such as the MCS, the Microgeneration Certification Scheme, if these guys are not registered on one of the main registers for these kind of things, do not touch them. Be very careful even if they are, because even then, some of these guys, a lot of them will be okay doing domestic type schemes, but they won't be particularly familiar with commercial type schemes. So have a look for all the registers where these people should be on. If you don't find them on, I would not touch them. But the registers do cover the whole country. And you could also look at people like RECC, Renewable Energy, again, certification schemes. Have a look on these websites and look for people who are certified, because they've bothered to put themselves through these certifications. So at least you know they've tried to make the effort. But it is, unfortunately, there's a lot of cowboys out there in this way.
So if I've put links in the chat into CIBSE and the MCS accredited list, and then the other one was the RECC.
Yeah.
Have I missed any, or are those the main three?
Try those. I mean, they're the ones really that are kind of the ones that are doing this well. I mean, to be honest, the type of heat pumps you're going to get are all from pretty good manufacturers. They are going to be people like Mitsubishi and Daikin and Valent, basically the same people, a lot of the same people who produce gas boilers. They've all moved into this as well. So I wouldn't have too many doubts about the heat pump itself. The key thing is whether your installer recognises the application and whether they advise you correctly on whether it's a sensible application and they install it in the right way. A heat pump can be installed, which is perfectly good, but if they ask it to do too hot a temperature and too high a work, it will just cost you an arm and a leg. And that's the bit that these guys don't necessarily understand.
Brilliant, thank you. The next question is about case studies. Are there any case studies of heat pumps installed in churches where the actual reduction in annual carbon dioxide emissions has been calculated, taking into account the use of a supplementary heating system during colder months?
And you know, I've chatted to quite a few people during this exercise preparing this for you, and unfortunately virtually nobody seems to be monitoring the performance of these heat pumps. The Newcastle one, they are going to be, it's being done by a very good consultancy, and they are going to be monitoring it and I think producing a case study from it. But the ones I've been in touch with and everyone I've spoken to, the question's always been the same when I've said, have you been measuring it? Do you know what the COP is? And unfortunately, people seem to put them in. And I guess really, as long as the running costs have been roughly what they thought, nobody's bothered to check. So I haven't been able to find any information on actual genuine case studies on what they've done. Only really people have sort of said, oh, well, the costs are okay. But a lot of them have been done against oil-fired systems, and the costs usually will be okay against oil-fired. It's an expensive fuel as well. Natural gas is the problem because that is such a cheap fuel.
I'll put a link in the chat through to our case studies page, but I don't think any of them have the detail that question
No.
is suggesting. But you can see what we've got on our case studies page there. The next question, in fact, there's two very similar questions. The one that's here says, I've heard that electricity prices will drop and gas prices will rise. Is this so? And then there's a similar question further down that says, I hear the government is talking about moving some environmental taxes off electricity and onto gas. And can we get our politicians to take that issue seriously? So do you have a crystal ball about the future of electricity and gas prices?
I wish I did. I'd be sat on my yacht in the Med by now, wouldn't I? But yeah, I can sort of give you some steer on that. There is a lot of talk around this because if they're serious about 600,000 heat pumps going in, it is impossible with electricity costs that they are as they are now and gas costs as they are now. I mean, in reality, at the moment, you'll probably be offered a contract about 16 pence per unit a day electricity. It's about 3 pence gas. So we're now at over 5 times the cost. So nobody is going to replace a gas boiler with a heat pump if they've got a choice at the moment because the cost would be astronomical. So there is a lot of talk going on around as somebody mentioned, the green taxes, if you like, which are all on electricity. Electricity was always the dirty fuel because we generated it from coal and gas. So all of those taxes, the environmental taxes, went on to electricity historically. That has now changed, and as I said earlier, the emissions levels for gas and electricity now are pretty similar, but all the taxes are still sat on electricity, making it very expensive. And there is talk about moving some of those. The problem is going to be is if you suddenly need natural gas twice as expensive as it is perhaps and doubled it to 6p and brought electricity down by 3p, given that the vast majority of the UK still heat their homes on natural gas, I think there would literally be a revolution in the streets if everyone had their gas bills doubled. And you'd probably put half the UK into fuel poverty overnight. So my personal opinion, and it's only my personal opinion, I cannot see that happening because the downside of that is enormous. It's not just going to drive behaviour, that really would hurt people in their pockets. They are looking seriously, though, at bringing the costs of electricity down, and there's been a number of things mooted there, one of which is that those taxes will come off electricity and go on to general taxation instead. That's a possibility. They are going to gradually try to make gas a little bit more expensive, and the levies, climate change levy, for instance, that is gradually being raised on gas over time. So it'll be equal to electric by 2025. But it's a very gradual process, so we don't see any big hit because of that domestic use of gas. So I'd be surprised if there's a massive swap over where they literally take it off one onto the other. I think the outcry will be huge on that at the moment. But they are talking about bringing that cost of electric down for heat pumps. And there are various things being mentioned, such as for people who are willing to take heat pumps for domestic purposes, they will be given a lower electricity tariff if they do that. So I think they're looking at a lot of other different ways of doing it because you're right, the point is nobody's going to take a heat pump on if they know it's going to double or triple their costs against gas, and that's the reality. So.
Okay. Amazingly, we still have 25 questions and 7 minutes. So we're going to have to try and be on it now. I don't think we're going to get to the end to manage everyone's expectations. Right, for air source heat pumps, how much contribution to running costs can be made by a solar panel scheme? Can you talk about solar panels as well as heat pumps?
Yeah, quite a lot. Obviously, the ideal is to sort of put solar panels on your roof to produce electricity on site, and that helps with the heat pump. Definitely, the more you can put on, obviously, the better it would be. But just remember, the one slight problem with solar is it produces the least of its electricity during the winter months. And that's actually when your heat pump will be working its hardest. So they're not the best match, unfortunately, because 70% of solar output is produced in 5 months of the year out during our summer. And that's probably when your heat pump is doing the least work. But it will definitely help offset the cost, and it's definitely worth doing as a joint sort of project.
Oh, what an interesting question. The next one is just clarifying, are there any ecological impacts from pulling the heat from the air, ground and water? Are we taking out enough heat that it actually affects the local environment?
It's not being thought of at the moment to be doing that, but obviously we don't have many heat pumps around the place. I think it's one of those questions that's being asked a little bit, and I think it's probably one that'll only be answered in the long run. Some of you may be familiar with name's just gone. The massive domes in Cornwall. Eden Project. They're actually going to drill geothermal boreholes down about 4 or 5 miles and bring up heat from that level, and actually it's hot enough to produce steam. And they're going to heat all the biodomes down there. The whole site is going to be heated from geothermal. So you can take it to the nth degree of that. Now, it's only when we get that we'll start to realise, I suppose, if we have any impact. But at the moment, it's not thought there will be. From us just taking some heat out of the ground. We're pretty limited in what we're taking, really.
And using your fridge analogy at the beginning, running the fridge doesn't make an enormous difference to the temperature of the kitchen, does it? It's only when you're very near it you can feel that warmth. So
in general, although if you're in a sealed room, I sort of audit lots of hotels and buildings, and their kitchens are roasting hot because they'll have 5 or 6 of them all putting heat into a closed room. So as long as you've got the ventilation, yeah, fine.
The next question says, we have a large medieval church. Are there any examples of churches which have used heat pumps? I'm beginning to feel that it's not for us. So Kate, if I find the link to our renewables map, we have a map on our website that has all of the installations that we know of. I'll just put that in the chat. And when you go onto that map, you can filter it. So you can look for the listing of the church, and you can look for the diocese, and you can look for which different technology they've used. So I'd say have a look on that map and see if you can find another church like yours that's got one. And then that link to the case studies, there's a case study there of a successful ground source heat pump installation in a church.
There are definitely, you can do it in big stone churches, but again, it's water temperatures. Newcastle Cathedral is a big one like that, but it's temperatures is the key.
And the next question, it touches on such an important issue in terms of what I think people need to kind of take away from this session. It says, from what I've heard, it sounds like heat pumps are more suited for a building used throughout the week rather than one used only for a few hours on a Sunday. Is that correct? And I think the answer to that is a pretty simple yes, isn't it?
It is, yes. A lot of the one thing I would say is the churches I spoke to, every one of them said the same thing. They all wanted their churches to be used right throughout the week. Newcastle Cathedral, the whole point is that the church will be used constantly, night and day. And that's why it suited them. They all said the same thing. They wanted their churches in constant use, so the heat pumps made sense. So you are right. They're not great for Sunday service only kind of thing.
Yeah. And the next question is very similar. So I think we might say that we've answered that. It says, I've heard that heat pumps work best if providing background heating all the time. Is that right?
Yeah, because they don't produce heat that quickly. They're not like gas boilers. They will take time. So you are better off having them producing regular background heat. And it's why you have these big hot water storage tanks as well to do
that. Can an air source heat pump be installed on a flat roof without too much of an impact on efficiency? Does it matter where?
Not particularly. The key thing is you do want to have good airflow across them. You don't want them in an area where they haven't got clean airflow, because you need that fresh air coming across them to actually remove that heat from there. There is actually a school of thought, though, that actually says if you can feed hot air onto them, they'll actually be far more efficient because the air they're drawing is hotter. So if they can be placed near another heat source, that might actually sort of potentially help them.
Now, let me look just before once. This might be our last question. It says...
I'm happy to go on a bit if you want, Catherine. It's no problem. If you want to do an extra 5 minutes, it's fine.
Oh, well, that's very kind of you. Thank you, Mark. In which case, I'll say to everyone, if you need to get away bang on one, then obviously do. But otherwise, if Mark's happy to hang on and you've still got a question in the queue, please do stay. You touched on the question of if the heat pump was also producing the hot water for the bathrooms and the kitchens, that there could be an issue around Legionella there. And there's just a question here. Does lower domestic hot water temperature at 60 degrees have Legionella issues?
Yes, particularly stored hot water. That's the big issue, is if you're storing hot water. Legionella, for the tests for that, is you need to have at least 50 degrees at the tap within 1 minute of starting to run it. That's the standard Legionella test. So everyone tends to hold domestic hot water at 60 degrees to make sure that the taps that are furthest away will run at 50. below 50 degrees, Legionella starts breeding. So if you're holding hot water at less than 50 degrees, particularly in old tanks, you're likely to get an issue. That is the potential. Above 60 degrees, you get kill of Legionella. Once you drop below 50, it starts to breed. Gets into its temperature range. So you do need to be careful. Legionella is spread through that kind of vapor, so showers and things like that, rather than anything else. So to be honest, sinks that are run is not necessarily going to produce a lot of vapor for you to breathe in, but you do need to be careful.
And I think for most church installations, the heat pump would be doing the heating, but then you'd have a separate point of use water heater above the sinks for producing washing hands, and an urn for making tea. So it probably wouldn't be the same.
I would suggest you do that specifically, because again, you probably don't need large volumes of hot water all the time. So separate the systems out, and then you can drop the temperature on your heating system, makes the pump more efficient.
The next question is about costs. Now, I don't know if this question was posed before you got to that bit of your webinar. It says, can you indicate the range of costs for an air source pump compared with a ground source for the same size of building? I have in mind a fairly typical church hall. So when you were talking about costs, you said for an 80 kilowatt unit, that would be quite a large one, right?
Yeah, that would be a decent size one. I mean, that's about perhaps 3 to 4 times the size of a normal gas boiler if you'd have in a house. So
if I'm picturing a standard church hall, I'm sure you've been in many over your life, would 80 kilowatt be the kind of thing we'd be looking for a church hall, or would that be?
Yeah, might well be, or maybe 345, something like that. It'd be that kind of setup, I would have thought. Yeah.
And you said in your cost that for that 80 kilowatt heat, 40 to 50,000 pounds if it was an air source heat pump, 80 to 90,000 pounds for the unit, for the ground source heat pump, but then the groundworks on top of that.
Yeah, and you can see those trenches that have to be dug. You can see where the extra cost is for the ground source. Yeah.
But then the ground source heat pump likely to be more efficient when it's running.
Probably will be. Yeah, certainly seasonally wise, it'll probably be better because the heat source is more constant.
Yeah. The next question is about hydrogen pumps. Hydrogen pumps being backed by the government as more efficient than heat pumps. Are we considering these? I haven't heard of a hydrogen pump. You get hydrogen boilers.
Hydrogen pump, or what is meant by a hydrogen pump there. Hydrogen is being considered by the government as an alternative heat source, but that basically, the hydrogen would be in our gas grid. So we would basically replace all of our natural gas, or a percentage of it, with hydrogen in our grid. So our boilers would burn hydrogen. The problem is, at the moment, our existing gas boilers anywhere will only burn about 20% of hydrogen and 80% natural gas before they stop working. So every single basically heat element in the whole country would have to be changed to work off pure hydrogen, or anything more than 20% hydrogen on the grid. There's lots of things going on at the moment. There's tests going on. There's a little village has been built up in the northeast, which is actually going to trial running purely on hydrogen on a dedicated network. The first hydrogen village is hoped to be sort of looked at by 2025. There is a university up north as well, which is also running, I think, the whole campus to test on hydrogen. There's lots of things happening with it, but to send the whole gas grid over to hydrogen is a very, very long-term view. Lots of different problems. Hydrogen's got much lower CV than gas, so you'd need at least twice as much of it. And also it leaks more easily than gas, the natural gas does. So there's a lot of issues around hydrogen. So it's part of the government's overall strategy, but it's unlikely to be anything in the very short term.
Then we have a question that says, what is the largest air source heat pump that can be installed on a typical 3-phase electrical system, taking account of the low coefficient of performance achieved in cold weather?
On a 3-phase, I mean, there's no limit. It depends on what your 3-phase system is. Your electrical system, they'll either be single phase, 240 volts, or 3-phase. But you will tell a local electricity company how big you want that supply to be. So if it's not big enough already, you would go back to them and say, I want to install some heat pumps. Can I have a bigger, cable coming into my building? Can I have a bigger supply? So there isn't a limit on a 3-phase electrical supply as such. It's what your local electricity company provides you with.
The question, really interesting question about vandalism. I'm concerned about the amount of kit outside and the risk of vandalism. How tamper-proof are they? The fencing around the Bristol example wouldn't do the job here. Do you have any examples of them being stolen or interfered with?
The units themselves, they're not going to be stolen as such. I never come across one like that because they are bolted down and they obviously piped up and fixed and everything else. But you're absolutely right. If you've got a problem with vandalism, people will put their boots through and they'll kick them, they'll smash them. They're not going to stand up to that at all. Very often these units are put on the roof or elevated up, so they're out of reach and they're not on the ground. The pictures I showed, there obviously were some. But yes, very often, certainly on commercial buildings, these will very often be up on the roof to avoid that kind of issue. So yes, they're not tamper-proof as such in any way. They can be smashed if someone really wants to have a go at them. And you've obviously got live electric in that system as well.
What a sad thing to have to think about that potential problem.
Yeah.
A question that says, is 16 degrees warm enough to remove coats comfortably? Does the church feel warm at that temperature, or would some churches want it to be warmer?
You'd probably want it to be warmer realistically. If you sat still in 16 degrees, you'd probably feel cold. That's not, your average house would be at about 20 to 22 degrees. So it wouldn't be like sitting in your house, certainly. But I know when I spoke to the designer for Newcastle, they said that's what they're going to go for. It's just meant to be background heat to mean the place is comfortable rather than, really kind of sat there warm necessarily. So, yeah.
Are air source heat pumps noisy?
Not particularly. No, they're no noisier than an air conditioning system. I mean, if you stood next to one, you'll hear the fan running and a little compressor running in them. But they're not massively noisy, and actually they do quote noise levels on all of the technical specifications for them. So they're certainly not going to have ear defenders on, or if you're inside a building, you wouldn't hear the unit outside particularly, no.
I've heard that comment. I've been asked it many times, but are they noisy? But the people I know that have got air source heat pumps have all said no, not at all. You'd have to really go near them and listen out for it.
I mean, like anything, because it's a rotating element, if it's not maintained, they become noisy eventually because the bearings on the fans go and things, and then they rattle. But that will be an old one or one that's not maintained. When they're new, they shouldn't be particularly noisy now.
Right. Are there hybrid systems that switch from air to ground from summer to winter?
You could do both if you chose to. I'm not sure why you'd do that, but yeah, that's just a control system, to be honest. If you wanted to put both in, you'd just have a control system that switched one off and switched one on. Yeah, it would, if you wanted it done, it could be done. Yeah.
It would be a bit of an expensive habit, though, wouldn't it, to install?
It would, yeah. And realistically, if you've got the ground source, you don't need the air source. So.
Oh, we have another crystal ball question. Do you know what? I'm just looking at the time. I think I might make this the last question.
I'm happy to keep going. Don't worry. If you want to get them answered, I'm happy. It's no problem.
All right then. All right. I believe that in 2025, the government is banning installation of new gas boilers in new build domestic properties. Is that likely to apply to churches at some time? So this is another crystal ball government policy question about.
It is a bit, and again,
the date.
For me, again, it's really based around that idea of sort of how logical, not so much how logical, but how practical this is. You've probably noticed that what the government said is they're talking about domestic properties, because the reality is to try and heat larger commercial buildings where you might have 200, 300, 400 kilowatt boilers, there is not an easy alternative to that at the moment. And a lot of churches will have boilers which are reasonable sized, 100, 200 kilowatts. It's not that simple to just bolt the heat pump in, whereas for most domestic properties, the insulation levels can be raised and it is doable for most domestic properties. And obviously what they're talking about is new builds. I'm not convinced we'll see the same laws applying to commercial and larger applications, just purely because it's not as easy to do. So I think they'll probably focus on domestic first, and maybe you'll see something about commercial and church and larger type premises a bit further down the line. That'd be my own suspicion. At the moment, they're not saying anything one way or the other. So they're only talking about domestic premises because that's where it comes from.
It does have to come, though. I mean, it's a question of time, isn't it? Because the government has signed up for net zero by 2050, 78% reduction by 2035. Yes. That's only achievable if we decarbonise heat. So
It is, yeah, and heat and transport are the two areas so far that have seen very little decarbonisation. It's all been on electricity generation. So yeah, they have to, but it's a real balancing act this between the fact that they know that heat pumps are not as cheap to run as gas boilers. So for anyone who's off grid, oil, LPG tanks, that kind of stuff, this works now. But for your standard person's house or business that has got a gas boiler, making them put heat pumps in will put their costs up. And I think there's a sort of balancing act needs to be done between the two. So,
practical question: how much space is needed inside for the pump?
It can be quite a lot of space. You saw earlier those big units. There's the standard little air conditioning unit that goes somewhere, but there is quite a big sort of unit, which I would suggest is probably something like the size of a single wardrobe. That's the heat pump itself. And then potentially, as you saw by some of the installations, a lot of people will have large hot water tanks as well, 1,000 or 2,000 litres of stored water to allow it to sort of go over the peaks and troughs. So they do need a bit of space. They're not tiny. Yeah.
Will the renewable heat incentive apply to vicarages?
If they are classed as domestic, yeah, the domestic RHI is staying until next April, but then that's going as well. It was extended for a year. So it's on anything that would be classed as a single domestic property. That's the way the RHI is applied.
Shouldn't cost comparisons include complete installation, including change to emitters, i.e. bigger radiators, not just the heat pump, compared with a gas or oil boiler?
Yeah, absolutely, definitely. But the trouble is that is purely down to the individual sites. The installation costs will be very site specific because it depends where the units are positioned, whether they got to go on a roof, they're ground mounted, how long the cable and pipe runs are, how you're integrating into an existing system. Are the existing emitters good, bad, or indifferent? So unfortunately, all we can give you is the sort of guide on the pump prices themselves, because the installation costs, you'll have to get a quote on that one. So
presumably it is better to site air source heat pumps on south-facing walls rather than north, as they are warmer.
Yeah, and as we said earlier, if you can actually get them near another heat source in a way, then if the air surrounding them, the warmer the air is surrounding the actual outside element of the heat pump, the more efficient they will run, because the less they have to lift the temperature. So like we saw on those graphs earlier.
So the next question then is about the claims for the carbon savings. The claim for carbon savings need to be based on the marginal electricity generation, which will be methane for a long time. Do you agree?
I can see the point you're making, but the grid factors that we currently work off include that marginal sort of gas-fired power stations. And you're quite right, the last sort of 3 weeks, they've probably been 50% of the grid total sort of supply. And we've actually had about 3% coal-fired power stations on in the last few weeks because we've had no wind. So that is true, but as the grid decarbonises ultimately, you'll have less and less gas on the grid, and that's how the emissions factors are calculated. So yes, the gas is the one that switches off and on. That's quite right. That is the marginal fuel, but the way emissions is done is over the long-term annual average. So.
What an interesting question. If this is a fridge backwards, is there a technology that does both? So it makes the use of the heat at the back of the fridge for heating, or uses the cold from a heat pump for refrigeration. Has anyone come up with a cunning thing that does both?
Yeah, heat pumps are reversible. You can have a heat pump, which is one way, or you can have a reversible heat pump. And what it does is heating in the winter and cooling in the summer. So it does exactly that. The units are still there, the exactly the same evaporator and condenser, but all the system does is it reverses its flow. So what it actually does is takes heat out in the summer and it pulls heat in the winter. So yeah, you can have a reverse heat pump which actually does both at but not at the same time, but the same unit will do both. Yeah.
The next question is talking about the kind of hybrid system that you were discussing. Is it possible to have a heat pump system with a gas boiler top up for water using the existing radiator system?
Not really, no, because the problem with this is that the heat pump will heat the water up to its level, say 55 degrees. The boiler will then top it up to 70 to 75 to feed the radiators. So that bit's fine, and you think, great, a lot less gas, lovely. The trouble is that water is then fed back to the heat pump to be reheated again. And if the water gets back to the heat pump at 60 degrees already, which it probably would be 60 to 65 degrees, it's already higher than the heat pump wants to produce. So the heat pump does nothing. It goes back through to the gas boiler, and the gas boiler adds the 10 or 15 degrees on. So once the water's up the temperature initially, the gas boiler would then do all the work and the heat pump does nothing. So unfortunately, you've got to switch the one off and bring the other one on for periods of really cold temperatures, realistically. Yeah, because the gas boiler just takes over and does all the work.
There's a question, you mentioned something about something changing in April next year. What is it that changes really the cost of heat pumps? In fact, you mentioned two things, didn't you? One of which is the 115 heat grant.
Yeah, the RHI for domestic heat pumps finishes in April 22. The other one as well is the electricity tariff structures are changing in April 2022. So what we have at the moment, which is there's a high charge at peak times of the day, which is nominally between 4 and 7 on weekday afternoons, when everyone comes home and puts the lights on, the cooker, the telly. So that's when electricity is most expensive. And in theory, some people used to switch their heat pumps off then and run their gas boilers to give them a cheaper cost. But those peak tariffs are disappearing as of April 2022. So if somebody's trying to sell you one of these and says, oh, you can turn them off at that time, peak time, it'll save you money, as of next year, that won't work, that disappears. So.
Can heat pumps be made more effective by using the output of one as the higher temperature input of another?
They can, yes. This can be done. Some clever questions here. Yeah, it can be done. You can sort of do this as a staged lift in temperature. However, it does get to a point where to keep them in the sort of sensible COP, you would end up need potentially quite a chain of them. And obviously the capital costs then start to get quite astronomical. But it is perfectly feasible to have one heat pump raising water temperature up to say 35. Feed that 35 into another one and get it to lift again and make them more efficient that way. The reason why it's not done really very often is capital cost, because these are not cheap to buy. At the moment, you know, people are stuck with gas boilers. We haven't seen that yet, but I suspect we will see a bit of it. But there is probably a limit to how many steps you do before capital wise it becomes nonsensical. So.
Then the next question, I think, is about the directories that we suggested people look at to find qualified people. It says, how about EMA registered people? Is there a list somewhere? If that's the Energy Managers Association, is there a list somewhere that people could look at?
No, the Energy Managers Association is the people who do the work, people like me, rather than businesses that install it. So it's a professional association rather than anything else. So.
Okay. Well, we're down to 4 questions.
Okay.
What are the standards for connecting pipework and any potential issues? Is that any different from standard kind of plumbing pipework?
Not really, not as far as I'm aware of. It would be pretty similar. And to be honest, you'd have people like gas safe engineers doing a lot of this. They're the same guys who do the heat pumps as well. A lot of them will do both. So nothing that I'm aware of that's particularly standard. And it's the same as an air conditioning unit, really. It's pretty much identical to putting an air conditioning unit in. So,
are there any issues with the national grid having capacity to cope with a big switch from gas to electric?
A huge range of issues. This is one of the other things that constantly comes up. If we all suddenly start driving electric cars and we all suddenly start putting heat pumps in, the reality is our grid won't cope. But there's an awful lot of work going on in the background to strengthen our grids, make our grids far more flexible. So they will make far more use of local generation and battery storage and things like that. So, but it's become a huge issue to balance our grid. The cost of balancing our grid over the last year with COVID and the demands being up and down so much as we went into lockdown and out, the actual cost of balancing the grid has gone up by 4 times, and we all pay that cost ultimately. So there is a real issue for the grid, but as long as this happens in a sort of phased way over a period of time, there's a lot of plans in place to match it. But there is still that ultimate thing that, yes, if we all plugged our cars in at the same time and we all have heat pumps running on a winter's evening, how would we cope? And I don't think there's any sort of real firm answer to that one yet. Certainly not for 2050 type time scale anyway. So yeah.
This next question, I think, must be referring to when we talked about combining solar panels with a heat pump. It says, what about selling seasonal surplus electricity back to the grid?
Yeah, and with any electricity generation technology, if you generate more than you can use, you will sell the excess to the grid. Laws of physics says it will naturally flow back the other way anyway. However, the economics of selling to the grid is pretty rubbish. You will pay at the moment about 16p to buy a unit of energy, the daytime unit of electricity from the grid. To sell it back to the grid, the average kind of prices is around about 5 to 6p. So you don't get the same money going back because it hasn't got all the tariffs and the taxes attached to it. So the economics of selling back is pretty rubbish. So you don't want to do it unless you have to, really.
Oh, I'm going to have to challenge you a little bit there, just because in our context, one of the reasons for installing solar is missional, because of the church's mission to care for creation. Yep. So financially, I can't disagree with your logic that financially it makes sense to use every unit of electricity you generate in the church. But missionally, if we create extra electricity and that goes out and makes the grid cleaner, then we've achieved our aim.
And you know, if you're exporting to the grid, you can actually credit yourself with that carbon benefit of what you've exported to the grid as well, and reduce your own carbon footprint by the same amount. So the carbon benefits are there, definitely, yeah.
And the final question, it says, I've heard it's difficult to find engineers to maintain heat pumps. Is that true?
It is a bit at the moment, because again, this is a bit of a niche thing and it's not really, I guess, taken off massive mainstream at the moment. This is an industry in a way that we're almost going to have to create from scratch. And this is one of the benefits of doing this, is I think a lot of people would like us to become front runners so that we can make these things, export them, and actually be, you know, market leader, because there's a huge amount of jobs potential in this. But because it's not something we've historically done a lot of, most of the heat pumps we use are imported. So people like Mitsubishi, Daikin, you know, Japanese, German companies. So we import most of the equipment anyway. And there have been a very limited number of companies that install these. So that actually is a fair point at the moment. But obviously, as the deployment ramps up, so will the maintenance ramp up quite quickly. But again, I would warn people that just means there's room for the cowboys to jump in and say they know all about these things when they don't. So always try and work with someone who's been in the game for a while, not somebody who's just done it for a couple of months.
Right, we've got to the end of the questions. Thank you so much for your extra time, Mark. That's so kind of you. And 40 people stayed till the end, so they're obviously very interested in what you have to say.
It's for punishment, obviously, yeah.
I suspect a lot of people came today going, I've heard about heat pumps, but I don't really understand them. And you've really helped clarify for people what they are, when they work, when they don't work, and what to look out for if you're considering it. So thank you very much, Mark. And a reminder to everyone, as I said at the beginning, Mark's repeating this session again in the autumn. So if you're thinking, oh, I wish my colleague had come here today, there'll be the recording on our website, but they can also come along to the future dates. I'll send everybody the slides later this afternoon, and also all those links that were in the chat, and look forward to seeing you at one of our future topics. Goodbye, everyone. Thanks for coming.
Thank you very much.